Ready? Okay. Hello, everybody. This is the last talk of the workshop, and the speaker is Davide Dionese, talking about cooling routines for AGB winds.
Thank you. Hi, everyone. Thank you for making it to Friday afternoon, this conference. So yeah, I'm Davide, and I'm currently based in Brussels. I'm a PhD student working with Dionese, and I'm doing a joint PhD, and my first supervisor is Dorota, and she's in the University of Warsaw. So yeah, my talk will be about cooling routines in AGB winds. But first of all, let me have a very quick introduction on what's the main topic of my PhD. So I'm actually going to work on long secondary periods. Long secondary periods are oscillations in luminosity of evolved stars. So we already had plenty of introduction on AGBs. So LSPs are observed both in AGBs, red giants, even red supergiants. And the period there, they can be quite long, and the amplitude of these oscillations can be up to even 1 magnitude. And what we often observe in LSPs is this peculiar shape in which we see a decline in luminosity, which is quicker, and then a slow rise back to full luminosity. Yeah, of course, LSP, as the name suggests, it's a long secondary period. So every time that LSPs are observed, we also observe a primary period, which is usually the primary precession period, which in this plot is like the smaller wiggles, while the LSP is the larger oscillations. If we look at LSPs in infrared, often we observe interesting things. And what we see is a secondary eclipse that is not visible in the visible light. Sorry. And the origin of LSPs, so of these secondary periods, is still debated. And what mainly this argument seems to suggest is that actually these stars are actually binary systems. So we are looking at a AGB with a substellar companion. And the companion is indeed like a brown dwarf mass kind of companion. So it's very small, it's not directly visible, and it should be hidden in a dust cloud. And my PhD idea is to model these systems using phantom intensiphos to try and replicate the observations that we have of LSPs. So where do we start, or where do I start from? The wind models that we currently have, which is the wind setup in Phantom. It's basically the same models that Lionel was talking about this morning. So it's already been quite extensively used. And what I'm working on in these models now is improving the cooling. Why do we need cooling in our models? First of all, because we need dust. And we need dust because AGBs, as you have already learned by now, they are dust-driven winds. So we really need the dust to be able to naturally drive these winds and these outflows. And then also, I specifically need dust because to explain LSPs, we need this dust cloud to be orbiting around the companion. So we really need the presence of dust and extinction to be able to model LSPs. And also, yeah, as Lionel already mentioned this morning, in order to be able to accrete quite a lot of material around the companion, we need to cool down the gas. Otherwise, if it's too heat, if it's too hot, it will just expand automatically. It will not be able to focus. As of now, only H1 cooling is implemented, which, yeah, it's better than nothing, but it's probably still not enough. And it's only, it's not effective at low temperatures. So below 3000 Kelvin, it's basically disabled. So it's more complicated to reach a dust condensation temperature of 1500 Kelvin or so. The chemistry that we are using now, well, of course, to compute cooling rates, you start from some abundances, and to derive these abundances, as of now, we are using an equilibrium chemistry network, which is kind of simple. It's the same one that, again, they were talking about in the past talks. And it's very straightforward, and it's fast to compute. So you just start from the temperature and you fit the Janov tables, which are thermodynamical coefficients, and then you get partial pressures of all the molecules and elements that you want, and then you can derive the number densities. We had to tweak it a little bit compared to what was implemented until now, because it was only reaching, let's say, around 800 Kelvin. And now I extended it further down to lower temperatures, because we also need cooling and abundances and cooling at these lower temperatures. And this could kind of be already a source of error, because in general, equilibrium chemistry is not super accurate at low temperatures, and the fits that we're using are not particularly good below 500 Kelvin, but as a first approximation, this is what we're working with. And then finally, I can introduce my cooling rates. So these are the main coolants that I'm using, or like the main cooling processes. So we have water, we have CO, some atomic species, H2. And this is the same plot as before, showing the abundances. And now here we're looking at the cooling rates. So the H1 cooling, so-called H1 cooling that was already implemented, is this dark line here on the right. And as we can see, this is in function of temperature. It's only relevant at very high temperatures, so above 6,000 Kelvin or so. And with the new coolings that I implemented, we have much cooling also at lower temperatures. This chemical network is for a CO ratio of 1.7, so C-rich star. And here, what we can see is what are the most relevant cooling processes for different conditions of number density and temperature on the y-axis. And we are comparing it to plots from the literature from Wojtka 1996. And as you can see, we are kind of close. I mean, we get the most important ones. So we found again CO rotational cooling, CO vibrational cooling here. Above for high temperature, we have H1 cooling, so atomic cooling. And then here we have single atoms. It's not exactly the same. I mean, liquefy oxygen, but it's very similar. It's very close. And also the absolute value of the cooling in this region is quite close. And then we are still missing a couple of probably important species, for example, SIS and also HCN. And the idea is later on to extend our chemical network and also introduce these coolings. But for now, this is what we have. We can do the same thing for O-rich outflows, even though our chemical network is not thought to be accurate for O-rich dust or O-rich chemistry. And so, I mean, it's working. We have the coolings, and this is the same plot as before. And we can see that we have H2O cooling for low temperatures, but this is also will not yet be used because we don't have O-rich dust. And I tried to include the new cooling rates within the phantom, within the wind models that we have. And it's kind of working. It's very preliminary results. It's still a bit buggy, it's still a bit slow, still some things are not working, but we can compare it with the H1 cooling that was implemented until now. And we can see that previously, basically the gas was just cooling, like because it's expanding, basically, like follow its expansion. And now we are able to drop to lower temperature close to the star, which is what we need if we want to form dust close to the star and be able to naturally drive the winds. And now the second part of my talk, I will briefly discuss what I did for the first few months of my PhD. This is very specific and like deep work within Phantom, and I'm only saying these things here because everyone it's a very expert audience. So this is the input parameter file that what you can see in many of your input files. And there are a bunch of parameters that regulate the cooling. For instance, I-cooling method, and then a bunch of different coolings that you can use. And then if you look at I-cooling, what you can choose when you select your I-cooling, you can introduce, well, you can have no cooling, you can put your cooling in step, you can put it in force, and which one is better, which one should I use when I run my models? How do I know what's the difference? I can choose different integration methods, implicit, explicit, exact. Why shouldn't I use exact if it's exact? like how should I choose? And if I want to use other kinds of cooling, Gami, ISM, well, am I going to put them in step? I'm going to put them in force and implicit. As of now, as it is implemented now, Gami, ISM, and all of these ones are automatically explicit, which is probably not the best. So anyway, some clarification are needed here, I feel. And so to check on a few of these cooling routines, we implemented a shock test. This is actually, it was already there, but I guess it's been there for a long time and no one really used it because it's literally just basically an additional cooling function that is only used for this shock test. And well, it's activated by this flag. And it looks like basically a step function. So this is the cooling as function of the temperature. And you can see that at very high temperature, we have zero cooling. And then we have this like triangular cooling shape. And then for low temperature, once again, we have no cooling. And if we run the shock test, it looks like this. So basically it's a tube, one-dimensional tube with gas going towards the center and colliding. The two sides are colliding at the center and they are shocking. So this is the density as function of the position in the tube. So we have a high density central region, and then the shock is moving outwards. So this is the jump in the shock. This is the shock gas. Why do we want to use this particular shock test to check all the cooling routines? Because we have an analytical solution. So basically we can compute run our shock test using all the different cooling methods that we want and compare it with an actual analytical solution. This was from a paper from 2011, and it was a nightmare to get this solution. Like it took months. I guess also many people tried. At some point we managed. So what you can see here is once again the high density center region, which is low temperature, because after this is the shock, position of the shock, and then it cools down to the upstream temperature, pressure, and velocity. So one of the first problems is that the analytical solution that you get, it's actually stationary, so it's not moving, but the shock is moving. So you need to find a way, once the shock is formed, to be able to move your analytical solution in the location where the shock is. This seems like a really dumb problem, but later on it will prove not so trivial. Oh, well. Okay, and so what we decided as a first step is to shift this analytical solution according to the maximum temperature found in the phantom simulation. And while we are only comparing this portion of the shock, so above the shock jump and below the maximum, because this is really the shock profile, and to quantify the accuracy of our models, we use this loss function, which once again is an arbitrary choice and might prove important. So we can compare different integration methods. Lower is better because it's loss function. And what we can see is that, well, explicit proves to be quite worse than the others, but implicit seems to be the best, even though they are all very close. Why isn't the exact method the best one? Well, because exact and piecewise cooling are not really friends in this case. And why? I'll go a bit fast here. It's a bit technical, but like the idea is that exact cooling is dividing your temperature in a temperature grid, and then it's iterating over the temperature grid, and it's lowering, like going towards lower temperatures. And if at some point you have a cooling which is equal to 0, you're not able to cool anymore. So you will not be able to decrease your temperature anymore. So you stay at slight higher temperatures. So in the central region of our shock, we are not able to go down to the initial temperature because at some point we are not able to cool anymore. And this is why exact with this specific test is not ideal. We can increase the, we can make the temperature grid finer. And we can see that indeed we get better result because we are getting closer to the T0, which is the original temperature, central temperature. But why, if we keep increasing the temperature grid, at some point we get a worse result? It's not very clear. Probably it's due to the shifting, which is not ideal, just by comparing temperatures. So what we can do is create a better shifting, which is basically another loss function to compute what's the ideal shifting for every specific model. And we find the better results. So now the finer grid performs better, but the explicit method performs even better. So it's really not clear still which one is the best. What we can see though is that they are not massively different. They are in like this error, which is once again an arbitrary loss function. They're all in the same order of magnitude. If, for example, we check the resolution of our models, we can see that it has a massive, like a much larger effect on the same quantity as before, which is a loss function computed on the density. So increasing the resolution of the model really changes this value. Increasing the resolution also changes, but it is known that shocks are better resolved. Like you need high resolution to find shocks. So the shock width, which is basically the width of the shock, is much better resolved with higher resolutions. And it seems that changing the integration method is like doesn't change the shock width at all. So yes, there are differences between using these integration methods. I would say that implicit is the best because it's more stable and it's faster than exact. It depends exact how high you make your grid, but it's usually faster and it usually performs better. But these are, yeah, likely provisional results. And that's all from me. Thank you for listening.
Thank you very much, David, for your talk. So are there any questions from the audience?
Maybe just a quick comment. I mean, the implicit method is obviously the only one that doesn't have any time step constraint as well.
Yes.
So is that a good default?
Yes, I would think so. Yeah, it never gives error, like there is no issue with negative internal energy because, yeah, indeed.
There are questions? Well, no, that's David again.